Hi everyone, thank you very much for joining today. Still a few people filing in, and I imagine they will for the next couple of minutes, but we'll just get started on the introductory slides and then move on to Wenping's talk. Shortly Wenping will take over. Dr. Wenping Jiang from Geoscience Australia will be talking about the application of multi-scale magnetotelluric data to mineral exploration. But I just have a couple of slides to go through before we move to there. Firstly, I'd like to thank our corporate members, our Corporate Plus members, High Size, Total Seismic, VelSize, and our corporate members, Southern Geoscience Consultants, Transparent Earth Geophysics, Santos, and Doug. Huge thank you to the contributions that they make to our society and also to the Ascg Research Foundation, which helps support honours, masters and PhD students in geophysics. We really appreciate the support, and if anyone would like to join this list, please just reach out to us. I'd also like to thank our branch sponsors. So for the South Australian Northern Territory, New South Wales and WA branch, these help to make regular technical events happen. So thank you very much for the support. Throughout the talk, you can type questions into either the Q&A or the chat box, and we'll address those at the end. Alternatively, at the end, you can use the raise hand function if you'd like to ask a question through audio, but don't hesitate to ask those questions. We have a couple of webinars coming up. On the 26th of August, we have Richard Lynch, who will be talking about passive seismic applications of ambient noise interferometry for mineral exploration. And on the 2nd of September at 1 p.m. Eastern Standard Time, which will be a hybrid event also hosted at Geoscience Australia in Canberra, we have Jack Muir and Zhongwen Zhan, and they'll be talking about preconditioned compressive sensing for wave field reconstruction, applications to tomography, Helmholtz-Hodge decomposition, and distributed acoustic sensing. The link to register is not up yet for the second webinar, but it will be shortly, but just check out the Ascg website and the events page on there to register. Our virtual program for the AEGC conference came out yesterday. I've had a flick through and it looks fantastic. We've got 6 streams, 6 parallel streams of talks over 3 days. They'll be available on demand, and there'll be live sessions as well, and the Q&A sessions for all the talks will be live. So looks like a great program. So go ahead and check out the website, the AEGC website, and registrations are open, and for ASCG members, I think it's off the top of my head, about $350. So it's great value for that. We've got a range of benefits of becoming an ASCG member. They're listed here. I won't go through them all, but I just wanted to highlight our technical journal, Exploration Geophysics, and our magazine Preview. Helps keep you up to date with the latest geophysics research and news. And you get reduced entry to the AEGC conference, as I just mentioned as well. And for students, it's free to join, and for retirees and recent graduates, it's half price, so very affordable. And don't forget to follow us on social media, and I'll pop these links in the chat as well afterwards, so you'll get the latest news on there. And so with that, I'll hand over to Wenping, and I'll stop sharing and invite you to share, Wenping. So thank you very much for giving a talk, and we look forward to hearing about your work.
Pleasure. Well, can I get someone to confirm if you can see my screen now?
Yeah, that's perfect.
Yeah, thank you.
Thanks very much, Wenping.
First, I would like to acknowledge the efforts from my co-authors. We have put together a paper and submitted to the Journal of Geophysical International, and we appreciate the positive feedback from journal reviewers. First, we acknowledge the traditional owners of the land on which our work is undertaken and pay our respects to elders past and present. We would like to extend that respect to any Aboriginal and Torres Strait Islander people who join us today. I will start from this map showing the discovered mineral deposits in Australia. Most exploration activities occurred in the outcrop and the shallow basement. And the rest, about 80% of Australia, is covered by sedimentary basins and regolith with various depths. And this largely underexplored region presents an enormous opportunity and a challenge for discovery of new deposits in covered region. For some reason, okay. So the footprints of a mineral system is detectable at a variety of scales, from deposit to the entire Earth's lithosphere. And Magnetotellurics, or MT, is one of the few techniques that can provide multi-scale data sets to map the large mineral system. So from high frequency to low frequency, audio MT targets the top few thousand meters, which can be used to characterize cover. And broadband MT can be used to map crustal architecture. A long period MT can image the lithosphere to a depth of a few hundred kilometers. In Geoscience Australia, we have applied all these data to a broad range of programs, including national scale long period survey and regional scale broadband and AMT survey in prospective regions, and also camp scale drilling geophysics program. The national scale AusLAMP is a collaborative program between Geoscience Australia, state and the Northern Territory Geological Surveys, and a number of universities and research organizations. With effort from all these parties, we have completed about 1,300 sites, which is about 40% of all the planned sites. We aim to collect long period data at half degree grid spacing across the whole Australian continent. And datasets has been used to map the large-scale electroconductivity in the crust and mantle, and provide new information to understand the geology and tectonic history of the Australian plate. As part of Geoscience Australia's Exploring for the Future program, we have progressed significantly a larger coverage in the Northern Territory and West Queensland. And the first stage data were collected in a focused area between Tennant Creek and Mount Isa. In total, the first stage of data acquisition in this focused area were 173 sites. The resistivity model derived from this AusLAMP data on the left at a depth of 35 kilometers revealed conductivity anomalies in highly mineral endowed provinces, for example, Mount Isa, and also in greenfield regions where mineralization hasn't been recognized. For example, a conductor to the east of Tennant, to the east of the Tennant Creek, I might use the laser pointer. Yeah, here. And this conductive feature is a north trending conductor coincides with a number of large-scale structures interpreted from potential field data and seismic reflection data. And it may represent a source region, a fertile source region for mineral system. Then we planned infill MT survey in the East Tennant region. We designed the survey with 3 denser transects and also complemented by an array of 10 kilometer spacing between the transects. Additional sites were collected in the proposed drilling sites. So this approach facilitates 2D and 3D model with limited budget. Today, I will focus on the infill MT survey. My colleague, Jing Duan, will present another talk on the AusLAMP data and model later this year. So in the field, we collected the natural signal from magnetic and electric fields of the natural signal, and we use induction coils like this one to sample signals in audio MT and broadband MT range. And in in 3 directions, normally north, east, and vertical. For long period data, we use flux gate magnetometer like this one. And this magnetometer has 3 components integrated together. But it needs longer period deployment, so often need solar panel to power battery. For electric field, we use 2 pairs of electrodes to measure potentials divided by 100 meter. And the acquisition unit record time series data simultaneously. And also we normally bury or at least trench for broadband for the coils and bury the electrodes to protect from animals and also noise. For audio MT data, 2 hours recording in low noise environment could get enough data useful for modeling. For broadband, need normally overnight or even 2 days recording. And for long period, we normally deploy for weeks. So data processing involves pre-processing to remove bad data segments. Then Fourier transformation to convert time series data into frequency domain as a series spectrals. And in frequency domain, we use robot processing, including spectral analysis, remote referencing in this technique to compute impedance tensor, normally expressed as apparent resistivity and phase. Here shows a few examples from East Tennant survey. As we can see, the data are reasonably smoothing, good quality. But also, you may notice some data sets in the range of 10 to 20 seconds are masked off. That's because they are in the broadband, deadband range, where the natural signal are weak compared to the noise. So normally it's noisy data. And we mask off for modeling purpose to avoid introducing artifacts. From data itself, we can get some useful information. For example, penetration depths. is a function of apparent resistivity and the period. For a given period, the signals penetrate deeper in resistive earth material and less deeper in conductive material. So in principle, this parameter gives the signal decay over depth and also an insights of resistivity, resistivity structure in the subsurface. For example, we look at the penetration depth at a short period, 0.1 second, which indicate shallow resistivity structure. From this plot, we can see in the northwest region, the penetration depths are relatively shallower, indicating conductive sedimentary basin. And to the southeast, as deeper depths, indicating a thinner sedimentary basin overlying on resistive basement. Except this localized area around ET091 is actually a basement high. We could see it later in the model. At a longer period or deeper depths, the structure is totally different to the shallow structure as we expected. And from this plot, we can say a northwest trending corridor that's conductive corridor, which corresponds to the conductive feature revealed in the AusLAMP model. Also a localized conductor around ET95. And the MT data or MT response could also give information of the dimensionality and directionality, which we use the phase tensor to derive this information. Phase tensor is formalized as the ratio of imaginary and real parts of impedance tensor. It filters the local distortion and derives the regional structure underlying. So from phase tensor, we actually presented in a graphical, the graphical presentation, we could present as a circle or ellipse. An ideal, if it's a circle, that indicate a perfect 1D structure. If the ellipse is symmetrical ellipse, then that indicates 2D structure. If the ellipse is skewed, that indicates a 3D structure. And the skew angle beta, we call it skew angle, indicates the degree of asymmetry of an ellipse. Normally in practical, in real data set, if beta is less than 3 or 5 degrees, we could treat the structure as 2D structure. Because of data noise, we could never get 0 degrees. So the top two plots showing phase tensor at short periods. So as we can see, the skew angle very small, between 3 or 5 degrees. So we could say in the shallow structure is a mixture of 1D and 2D structure. But for the longer period, deeper depths, we could say some skew angle is out of the threshold. Most showing more than 3 or 5 degrees, with some still showing low skew angle. So that's mixture of 2D and 3D model, 3D structure. And the directionality, which we say strike angle, is critical for 2D model because we assume a 2D structure, then the conductivity only change over depth and one direction, which is across the regional strike. And from this tensor, we could derive theta, which gives the strike angle with a 90-degree ambiguity. But this ambiguity could be clarified by the geological strike, which we can say interpreted from magnetic and data is a north-west trending. So we determined the strike angle is 50 degrees. So now is the data inversion. Data inversion is a reverse process of forward modeling. It's more challenging because there's only one model can result in the observed data. For example, on the right, all these 3-layer models can fit a set of observation data. So this is the non-uniqueness inverse problem. So to solve the geophysical data inversion problem, we have 2 broad categories of methods. One is the deterministic methods, and the other one is probabilistic. A deterministic method is an optimizing approach. It strives to find the best single model that fits the data. It depends on initial parameter estimation and regularization. However, it provided limited information on model uncertainty. But compared to probabilistic methods, it's computationally less expensive. Although for large 3D models, it's still the computational demand is still very high. Then the probabilistic method doesn't settle on a single model, but sample millions of models. It doesn't depend on initial parameter estimation and no regularization. The result is the posterior distribution of all possible models. And uncertainty can be quantified from the distribution of the outcomes. And the computational is more expensive. That's the downside. That's why probabilistic model we often found to deal with 1D or 2D with fast forward modeling. Having said that, recently some researchers have developed a fast solution for 3D forward modeling problem, which is to construct an approximation or saturate model to avoid running a full forward model. So this approach may enable 3D data inversion in a probabilistic framework. Now we look at more details in the method, the regularized deterministic methods. Often the objective function contains model roughness, distance from a reference model or starting model. Then the data misfit terms and a Lagrange multiplier to balance the trade-off between data fit and regularization. So this inversion scheme results in a smooth model that fits the data with a bit tolerance. The smooth model is preferred structure, or we say minimum structure model, because we don't want artifacts in the model. So we only need just sufficiently fit data, but not noise. This principle has been widely adapted in most of the model schemes, including probabilistic sampling approach. So Bayesian inversion is a typical probabilistic inversion method. Bayesian inversion, it seeks to sample all the possible models from a posterior probability distribution defined by the Bayes rule, which include a prior probability distribution, which gives a prior information or knowledge or belief of the model supposed to be. Then a likelihood function, which gives how well or how possible a given model fit data, give the result data. Then we need a sampler to draw samples from the posterior probability distribution. Here we introduce a transdimensional or reversible jump Markov chain multicolor code. We applied to 1D MT data inversion. We named it RGMC MCMT code. The transdimensional aspect means the number of layers in the model is solved for, not predetermined. So the algorithm samples models over the sampling process is driven by data, self-parameterizing, and it adapts the minimum structure principle. It's naturally parsimonious, and it is parallelized using MPI. So we can run multiple microchains with each sampling million models. And we built it on an open source RGMCMC library developed by the Research School of Earth Science at ANU. We have made the code freely available on GitHub repository. And the details of the method you can find from publication by Ross Brody and myself. Now we look at the modeling results. First is the 3D model. On the right shows the preferred 3D model. So although the deterministic modeling approach produce a best model, but in practice, we often do sensitivity tests to produce a series of models. Then we systematically assessed the robustness of the model's features by testing starting model, smoothing factor, and using different discretization and data subsets. So the code that we used is the ModEM code developed by Oregon State University. And we applied the minimum structure nonlinear conjugate gradients algorithm, which is more efficient and reliable compared to other algorithms. And this preferred model achieved a normalized IMS misfit of 1.6 with the error floor of 5% of the square root of the diagonal components of the impedance tensor. We didn't use the vertical data, unfortunately, because the vertical data either very noisy or missing. because in the field, in the Barclay region, is often very windy. And the contractor used tripod to hold the vertical coil, then covered by a tarpaulin on top, which didn't work. So very noisy data. Also for the helicopter size, because the auger couldn't fit in the helicopter. So in those sites, the vertical data were not collected, which is a bit unfortunate because vertical data could give actual information, and it's free to local distortion. Now we look at the model. I think I have to go back to this way. Yeah, to show this animation. We can see this, the vertical slice. So we can see conductors in the lower crust and also conductive pathways extending to the surface. See, on the left, we show the 3 vertical slices. And we look at the plane wave depth slice at 2 kilometers. And for the conductors, we labeled them. You may notice some showing in some slides, some not in others because of the depth. So at 2 kilometers, then 5, 10, 15. So from this depth slice, we could see C2 and C3 actually form one conductor. Then broadband data normally could solve depths to 40 to around 40 to 60 kilometers, depending on local resistivity. So more conductive then would be a shallow depth resolved. This animation shows the conductive body with resistivity value less than 100 ohm meters to a depth of 40 kilometers. So we could say 2 larger conductors in the crust from mid crust to lower crust. Then a number of conductive pathways linking the lower conductor to the near surface. So similar structural constraints were observed in mineralized terrains and are associated with IOCG discoveries. For example, Olympic Dam and Mount Isa. Now we look at the impacts on mineral systems. We recognize 4 components essential for mineral deposit formation, including energy, which drives fluid migration, the favourable architecture, which allows energy and fluid propagation, then sources and depositional sites. Only if the 4 components come together in space and in time, a source is conveyed to depositional sites to form mineral deposits. And from the first, from AusLAMP model, we could say for a conductive zone, which may represent a fertile source region for mineral system. And from infill MT survey, we say conductive pathways linking deep conductive feature to the near surface, as where the major faults were marked by potential field data and seismic data. We also use the recently collected seismic data to further constrain the structural architecture. The data was collected as part of EFTF Berkeley, EFTF Berkeley deep seismic survey is a segment of this seismic line, which in line with some MT sites. Now we look at the interpretation on the top panel. The seismic data revealed the Glangro fault as a southeast deeping major crustal structure, which offsets small hole. And in its hanging wall is dominated by a series faults, and some of them interconnected in depths. And Lam fault is one of them. To the northwest of the Glangro fault, the structure is dominated by north deeping faults. And Christmas Hole fault is a major fault, which is transected in the mid crust. So compared to MT constraints, we could say the seismic interpretation is inconsistent with constraints provided by MT data. Further to a deeper depth from the passive seismic data mapped a lithosphere scale structural corridor in the East Tennant region, as shown by the contour of LAB. It shows a major gradient cross East Tennant region about with about 40 kilometer vertical offset cross 150 kilometer lateral distance. The background image is velocity image at 10 kilometer, showing the same northwest trending corridor. So this kind of architecture has been recognized to be associated with a large mineral system globally. Now we look at the new geochronological data still from legacy drill holes. This data suggests basement rocks in the East Tennant region are age equivalent to Warmanga province and Morphy province, which implies a shared tectonic driver. That is the 1850 man Tennant event. Then finally is at depositional sites. Modeled iron oxide alteration from potential field data shows hematite rich and magnetite rich alteration in the East Tennant region. And more encouragingly, we see schist with pervasive magnetite and hematite hydrothermal alteration in the legacy drill core, and minor copper with hematite. Then predictive mapping using these data sets highlighted the East Tennant fairway, which is prospective for IOCG type of mineral deposits. Then we planned East Tennant drilling program in partnership with Minix CRC and Northern Territory Geological Survey. Minix CRC is the world's largest mineral exploration collaboration between geological surveys and researchers from universities and the industry, with a funding of $220 million for 10 years. And the first two programs focus on drilling technology and the data collecting and technology. And the third program is a National Drilling Initiative, which undertakes drilling in explored region and aims to open up new frontier for mineral exploration undercover. So East Tennant drilling program is the very first NDI campaign. During drilling site planning or targeting, we inverted AMT data using the probabilistic methods we developed in-house. The purpose is to constrain the cover thickness for drilling targeting. Here shows one example at a proposed drill site. Left side showing model fit with data. Also, the model convergence history and a histogram of the number of layers in all the possible models. Then on the right, showing the posterior distribution of all the outcomes. Warm color showing higher probability. And also a change point histogram showing the layer, the model layer interface change. So we interpret the conductive weathered Georgina basin of the top few tens meters. Then moderately conductive, maybe with mixture of basalt from Calcul region province. Then more conductive, a more conductive layer. This conductive layer appeared in some of the sites. It could be the shale in South Nicholson Basin, or could be some conductive or even with groundwater in the Georgina Basin. So we are waiting for the drill core analysis then to improve the interpretation. But this spike, that's the contrast, shows inconsistent with the contrast from conductive sedimentary basin to resistive basement. This is quite certain interpreted as cover thickness. At this site is less than 200 meters. Okay. So there are more examples at proposed drill sites. For example, the first one only 70 meters, and second one about 220 meters. And the third one 400 meters, still drillable depth. But at site 15N, we see the conductive material and the third layer about 400 meters. And the possible top of basement could be as deep as 800 meters. So we moved this site to 12 kilometers northeast. And the last one is very interesting at site 127. So conductive from the near surface down to 2,000 meters. That's the resolution of AMT data with confidence. So this site, we will see the drill core. I think we had the final drill size at this MT sites. So from all the sites, Sorry, I don't know what's going on. Was I muted? Is that over time?
Nope, sorry, Wenping. We just had a little technical difficulty. You're back unmuted. Thanks.
Okay, that's all right. So let's look at this cover thickness map on the right. And this marked final drill sites with adjustment after we get some cover thickness insights from AMT data. So this map shows the cover is very much similar to the penetration depths in the shallow, in the short period we showed earlier. So, which demonstrates the consistency between data and the model. Another thing I'd like to point out is to the northeast of Golongro Fault, the cover thickness apparently is much thicker than the southeast side. So we would think this fault would be the boundary of the South Nicholson Basin, because South Nicholson Basin is covered by Georgina Basin and the Kakko Region Province. Previously, on the right, is boundary is interpreted from sparsely distributed drill hole, legacy drill hole, and the potential field data, which is relatively insensitive to depth. So we think from the new data, South Nicholson Basin is bounded by Golongro Fault. Is further constrained by the 2D model. So we can say the three 2D model sections from the three denser transects. And also we put Golongro Fault as the bold black line. So to the northwest, which is left, we can see apparently thicker cover, consistent in three models. And to the southeast, thinner cover. Also, we see conductor, which consistent to the 3D model. So the East Tennant program has completed 10 holes, 4,000 meter drilling. And our colleagues are working on comprehensive drill core analysis. We also have wireline logs. So the drill result will help to improve our understanding of cover sequence and also geological basement geology and mineral potential. We will also use the drill site to validate our models and to improve our geophysical interpretation. So this work, the work in the East Tennant region has generated significant impact on exploration industry. As shown in the tenements application, from 2018 to 2020, the tenement application has increased about 181%. So that's the last summary. First, the AusLAMP data highlighted a potential fertile source region for mineral systems. An infill MT survey revealed favourable conductive pathways in the crust. And AMT data effectively characterized the cover and assisted with stratigraphic drilling targeting So we conclude integration of geophysical data from multi-skilled surveys is an effective approach to skill reduction for mineral exploration in covered terrains. And last, I would like to acknowledge colleagues from the Origin University and made the mod-EM code available for our work. We also thank Malcolm and Ray from ANU for their assistance with the RGMCMC library. We also acknowledge resources from the National Computational Infrastructure Australia, NCI, and fundings from Exploring for the Future and the MINIX CRC and Northern Territory Geological Surveys. And thank you. Any
Great, thank
questions?
you so much, Wenping. That was a really fantastic talk. Apologies for accidentally putting you on mute. My computer decided it was a good time to just update.
Should I stop sharing now?
Yeah, you can stop sharing. Thank you.
It's okay.
So in terms of questions, so David Annette has said, great talk, Wenping. I have two questions. Can you comment on electrical anisotropy? Is this likely to have an influence on your results? And his second question concerns integration of the MT with the AEM surveys. Do you have any plans to develop a model for that?
Okay, can I answer the second question first?
Yep.
Yeah, we do have colleagues working on AEM interpretation and also with AMT AMT models to interpret the cover thickness, and we're planning to produce a cover thickness map for the East Tennant region. We have planned to invert AMT data with AEM data as joint inversion. We put a proposal in for the MINIX CRC. Hopefully we can find researcher and postgraduates to work with us on this plan. The first question.
With anisotropy, is it likely to have an influence on your results?
We haven't looked into it because for the code that we used doesn't deal with that problem. So it's yeah, it would be good in the future we could address that, but without doing it, we can't comment on the influence now.
Yeah. Next question. From Mark Duffett, is there any correspondence between the magnetite and hematite alteration inferred from potential fields and higher conductivity?
I remember there is a map showing, yeah, I didn't put them together. If we put together, we would see in the about at the location of the drills, the Lexi drill site DDH 005, in that localized region, that's where the conductor coming up to the near surface as shown in the MT model. That's also showed a few hematite and magnetite alteration showing in the same region. Yeah, we could put them all together to show the correlation.
Great, thank you. Grant, how long did the project that you presented today take?
The survey was planned, I think in May 2019, but didn't get started until July, August. Then then after that, that's about maybe eventually I think I got all the survey data was input AEGC conference. That might be September. So that time I got the data, then started to work on data cleaning up, the modeling. Then we presented some results in Christmas, just before Christmas, preliminary 2D results. Then later we released 3D in March 2020. Yeah, I think March 2020, we released the data. I can't remember, I released the model, I think. Yes. So all these models, including 1D probabilistic model results, they all released from GA portal and GA data catalog. Then, yeah. Yeah, I think that's about it. Let's see, survey planning from May, then to data model release to March 2020. Yeah, that's about the right time frame.
Yeah. Mike Barlow, with the national coverage made up of many surveys over many years, is there a need for Australian-wide calibration lines to tie it all together?
It means the AusLAMP data.
I guess all of the MT.
I guess, yeah. So the national scale MT data, yeah. The plan for calibration, I'm not aware if we have any plan, because the collaborative partnership, it covers quite a few different organizations, the Geological Service and universities. Basically, for each state geological service, especially the geological survey has strong capacity for MT modeling. Some publications, like from Kate, Stefan, and Graham, they already the publications are already out there. Yeah, and I don't know in the future we would have national scale data platform or calibration. I don't quite understand the calibration part of the AusLAMP survey. So could Mike clarify what he expects for the collaboration? Is that because for each parties, when we collect data, already go through the data QA/QC process, modeling, sensitivity tests, and interpretation by integrating with other data sets. So this part of the validation process for MT data and for the interpretation as well.
Yeah. I think that Mike said he will talk to you later about it, and thanks.
Okay then.
David Teal said, did you notice any wind effect from moving trees on the magnetic sensors? I think he actually posted an earlier version of this question because you mentioned with the vertical coils,
yes,
problems with wind, but I think his question was based around the buried coils near trees.
We avoid doing that. Yeah, as I showed the field layout, and we have the electrodes. Normally, we get we more concerned about the electric field because magnetic fields, especially for broadband survey, the size spacing maybe 2 kilometers, 5 kilometers. If the magnetic field data no good, we could compromise or replace with a nearby site because magnetic field doesn't change significantly over distance. But for electric fields, is more concerned about noise. So when we deploy 2 electrodes with 100-meter cable, if one of the electrodes close to a tree, then we would avoid doing that, because when the wind blowing the tree, the roots may cause noise for the electrodes. So that is one of the we have SOP, like standard operating procedure. That's one of the things we would tell contractor not to put instruments too close to a tree, under the tree or vegetation. Yeah.
Lots of thank yous, and you did a great talk and excellent presentation. We've got things from Mexico as well. Great to have international audience here. And comments, you're a great communicator of science and explain things very clearly, which I'll agree with.
Thank you. Thank you.
You've got still about 6 more questions there, so let me know if you get answering questions, but maybe we can quickly go through a couple more if that's all right. So from Masayab, we have, thanks for the great talk. Would you suggest using seismic interp to constrain MT models? Major faults look consistent on both models on one of your slides.
Yeah, if possible. Yeah, if we do collecting MT size along seismic lines. We did for quite a few in the past. For example, in Mount Isa region, and we also planning to do more. And also Geological Survey Queensland, they are planning. I think they just completed the survey along a seismic line. So the idea is to use seismic interpretation and MT model to constrain the structure. Yeah, then we would get more confidence, because they measure different property, then would give different insights, then could maximize the data potential for understanding geology and structure. Yeah.
Yep. Okay, is there any indication of a timeline for assays study release on the NDI holes?
On the NDI, yes, I think it's different session. It's a regional drilling section working on NDI, the whole borehole analysis. They started to release some results a few months ago. Yeah, if you search East Tennant drilling program, you could find a platform with 10 drill holes. Each has some results released already. Yeah, it's an ongoing process, and it started, I think, a few months ago. Yeah, maybe from early this year. Yeah, the drilling program completed just before Christmas. Then the drill core analysis started just straight after that. Then some results are also with colleagues from Northern Territory Geological Surveys. And our colleagues had a drill core sample, also workshop, something called drill core sample inspection or something. Yeah, they have run workshops and showed some results, then started to release, and there will be more coming.
Great. David Moore asked, as Tennant Creek is a known IOCG province, why was it not covered in more detail so it could be used as a training data set for the rest of the data?
Training, are we talking about machine learning?
I was wondering the same thing, but maybe he means as an example to sort of base your interpretation in other areas.
Yeah, actually, the idea is to use already recognized IOCG deposits in already discovered region like Olympic Dam and Mount Isa. In Mount Isa area, we did some work there. We had we had a paper published by GGR. We showed the conductive pathways, which and also a concurrent survey in 2016. We have more high resolution data. The model showed the Henry said moderate mining and Ernest Henry sites, they actually on top of conductors in the model. So we used this already recognized mine sites, which in spatially correlation with conductors in the empty model to establish the concept. So then in East Tennant, before there is greenfield areas covered region. So we hope East Tennant would be a new example which established the model and the mineralization could be the same happened in East Tennant, then that would consolidate our established established in mineralized region. Yeah.
So there's 3 more questions. Are you happy to answer them now, or I can email them if you like?
Yeah, you can email me if we're running out of time. Yeah, I'm happy to answer by email. Thank you, Kay.
Yeah, no worries. And were you happy for this talk to go up on the YouTube channel? We just had that question come through as well.
Yeah, sure. I'm happy for that.
Great. All right. Well, yeah, thank you very much for all the excellent questions that have come through. And I'm sure Wenping will be happy to answer any others via email, and also through the ones that are here. Yeah, that was an excellent presentation, and yeah, very well presented. Yeah,
thank you.
Work and,
but still feel lack of engagement with audience.
The webinar format.
Yeah,
well,
still feel
there
different.
definitely are people on the other end. This has certainly been one of the most popular webinars. So yeah, thank you very much.
I'm feeling like I'm talking to myself.
It would be a cruel joke if there was no one else on here and I hadn't told you, but there are. Right. Thank you very much, and thanks everyone for joining, and have a nice afternoon or sleep, or depending what time of it is in wherever you are in the world. So yeah, see you everyone.
Yeah, see you. Thanks. Bye.